Okay, if slope stands for the slope of the graph in the y equals y star plane above the point x star y star, then a unit vector, or a vector in the direction of that slope, or a vector tangent to the surface, to the sphere at that point, could be just plain old I plus slope times k. Okay, now why does this vector have a slope that's equal to slope? Well, it's because the rise is in the k direction, the run is in the I direction. What's the rise of this vector? It's slope. It's the coefficient of k. So the rise is slope. What's the run? Well, it's just vector I plus slope times k. Well, it's the same as 1I plus slope times k. The run is 1, so the slope is what? Rise over run equals slope over 1 equals slope. So this vector does have slope equal to our slope. Now, just talking slope, but I didn't want to get into a lot of confusing notation. The slope is partial of z with respect to x evaluated at x star y star. That's what our slope is, so that our tangent vector is I plus partial of z with respect to x evaluated at x star y star times k. Now, by complete analogy, we can slice the plane, or we can slice our space this way through the point x star y star for x equal constant, and our slope is going to be the partial derivative with respect to y, because it's y that's changing along this line. And by analogy and by reasoning it out and drawing it, make sure you're comfortable with it, make sure you understand it, the tangent vector in the plane x equals x star would be j plus partial z with respect to y, evaluated at x star y star. Now we have two tangent vectors in different directions. Vectors tangent to the point on the surface of the sphere that lies directly above the point x star y star. What's the orientation of the sphere at that point? Well, what's a normal vector? Normal to the plane of the top of our wood block model. Normal to the plane of the top, which would be normal to the sphere, is just the cross product of these two tangent vectors. Okay, we get the normal by taking the cross product of two tangent vectors. So we take the cross product, and here's what we get. And that's just completely straightforward. I'm not going to explain that calculation, except to say that I cross j is k, and I cross k is negative j, and k cross j is negative I. That's where you get this. And k cross k, of course, is 0. Okay, well, there's our normal vector. Now what we have is above the delta x by delta y rectangle down here in the plane, the xy plane, we go up here. Yeah, I'll just draw it. We have this surface that maybe looks something like this. And I haven't drawn that top very well, but the top is at some angle. Now, it's on a sphere, and the way I drew the point in the first quadrant of the xy plane, the x star y star, the slope of this thing is actually negative in the x direction and negative in the y direction. So really, the graph would kind of be coming down here, be over here like this. So something, well, that's all messed up. Anyhow, you get the idea. And there's some normal vector. And that's not a good drawing, but you get the idea. So let me just draw. Let's make one more attempt to draw this reasonably well. Okay, this point will be somewhat low, and this point will be even lower than this one. and we're going to have something like this. Now we're going to come down parallel to this, and I kind of missed the parallel, but you get the idea. Okay, something like this, kind of tilted this way and this way. And now our normal vector can be understood as something that's kind of coming out in the direction away from the origin, not, well actually it is going to be directly away from the origin because we're on a sphere. In general, you know, with other surfaces that's not going to be the case. Okay, we want to know how the area of the top of this wood block figure is related to the area of the base. And the base, of course, is delta y by delta x. So the base area is delta y times delta x. What's the area of this thing? That's going to be very relevant to figuring out the total area of the sphere, total surface area of the sphere. This is part of the surface of the sphere, or it's a small plane segment that's very close to the corresponding area of the sphere above this rectangle. We get a handle on that by determining the angle between this normal vector and the vertical, which would be the angle between the normal vector and the k vector. And that's really easy. Here's the normal vector. You would just take the dot product of the normal vector with the k vector and divide by the product of the magnitudes. And this is so straightforward, I'm not going to write it out, I'm not going to explain it. It's just very clear that the magnitude of n is 1 plus zy squared plus zx squared. Magnitude of k is a unit vector, it's 1. K dot n, okay, here's n, dot that with k, what do you get? You get 1. You see that yourself, okay? Now this tells me then that if we look at this surface from the correct angle, from the most advantageous angle for understanding the ratio of the surface area, that the surface up here, I'll make this red and I'll make this red, okay? This is our surface viewed from a point in the plane perpendicular to the k and n vectors, okay? And we're going to have some angle between k and our vector, between the vertical, not vertical and our vector, between the vertical and our plane. Now I'm just doing a plausibility argument right now. We can make it more rigorous, but we were close to the end of the class and plausibility is good enough for right now. If this angle is theta, then the area up here is in the same ratio to the area down here as this side is to this side. Okay, so we just take the ratio of this hypotenuse to this segment, which is one of the adjacent sides, it's the same as one of the adjacent sides. And what I get here, and I haven't looked this up to be sure because I kind of always remembered this as being a secant, but I think I'm confusing something because I don't remember these things. I can always rederive them, but that's getting to be a little iffy as I get older. It appears to me that the ratio of this side to this side, well, here's your angle theta. Well, here's your angle theta because this side is a traversal of two parallel lines, so this angle here has to equal this angle here. They're alternate interior angles of a traversal. So this angle's the same, and the ratio of this side to the hypotenuse, well, this side is opposite the angle theta, so the ratio of this side to the hypotenuse is the sine of theta. So the ratio of the hypotenuse to this side, which I call the opposite side, side opposite angle theta, is reciprocal of sine theta, and that's cosecant theta. Okay, now that makes a certain amount of sense. Okay, if theta was 90 degrees, then the hypotenuse would correspond to this side, would coincide with this side. If the theta is 90 degrees, that means the top of this thing is horizontal, so it's just parallel to the base of this rectangle. So it's going to have the same area because you're going up here perpendicular to the xy plane, and now you're intercepting it with a plane that's parallel to the xy plane and all that, and it's very clear that the area of the top would be the same as the area of the base. Okay, it'd be a rectangular solid if this angle was 90 degrees. And if this angle was 90 degrees, the sine of theta would be 1, so that the reciprocal of the sine theta would be 1, or if you prefer, the cosecant of theta would be 1, and the two areas would again be the same. As this angle moves away from, or as this orientation moves away from the horizontal, the orientation of the surface, the sine theta decreases and the cosecant of theta gets bigger. You have more area here than you have here. You have more length here than you have here, meaning you're going to have more area on top than you have down in the plane. And that ratio should be the cosecant of theta, even though I remembered it being the secant of theta. But the secant of theta wouldn't make any sense if it was a secant of this angle. Now the only thing I'm thinking is maybe, for some reason I can't fathom, but you know, the depth of my thinking isn't what it once was, so I don't fathom everything I might have. Maybe theta is supposed to be the angle between here and here, so it'd be this angle, in which case you would have a secant. And that's kind of the way you do it when you're doing arc length in the plane. I'm going to stick with this for right now, but if you change what you mean by the angle theta, you would get a secant. It simply makes a lot more sense to think of theta as the angle between vertical and the normal to the plane, because that's really easy to calculate. It doesn't make sense to convert that to a different angle. But there could be something I'm not thinking of. I'm sure there is. Okay, well there it is.